All right, today we're going to pull back the curtain on the invisible world of structural engineering. We're talking about the hidden forces and, honestly, the brilliant little components that hold our entire world together, from the tallest skyscrapers you can imagine to the longest bridges. Let's get into it.
You know, when you see a structure like this, it is just awe-inspiring. It's so easy to be blown away by the sheer scale of it. But while you and I are just driving over it, maybe listening to music, that bridge is fighting a constant, colossal battle against gravity and a dozen other forces, every single second of every single day.
So that really is the big question, isn't it? What's the secret? How do these massive things just stay standing? Well, the answer is both way simpler and a whole lot more clever than you might think. See, the secret isn't just in the giant steel beams or those massive concrete pillars. The real magic, the true unsung heroes of this whole story, are the points where the structure actually meets the ground. It all comes down to the connections, or as engineers call them, the supports.
The best way to think about supports is that they're like translators between the structure and the earth itself. They take all the weight, all the wind, all the vibrations from traffic, and they safely channel all of those forces down into the ground, making sure the whole thing stays perfectly stable.
Now, to wrangle all these different forces, engineers have a whole toolkit of different support types. We're going to meet the three main players, the big characters that you're going to find in pretty much every major structure out there.
First up, we've got the fixed support. This one is, well, it's the strong, silent type. Imagine a flagpole that's been set deep in a big block of concrete. It can't shift side to side, it can't move up or down, and, this is critical, it can't tilt or rotate. It is completely, totally locked in place.
So the crucial thing to get here is that a fixed support resists, well, everything. It stops any vertical movement, any horizontal movement, and it also stops any twisting or rotating, a force that engineers call a moment. It provides total, absolute restraint.
Okay, next we have the pin support, which is also called a hinge. And you already know exactly what this is. The perfect example is a door hinge. The door itself can't move up, down, or sideways out of its frame, right? But it is totally free to swing or to rotate.
So you see the huge difference here? A pin support will resist any vertical or horizontal forces, but it gives zero resistance to rotation. And that freedom to rotate, that's not a weakness, it's a feature, and it's an incredibly useful one in all sorts of designs.
And our third key player is the roller support. Now this one is really special. It's designed to resist force in only one direction, usually up and down, while being completely free to move in another, kind of like a wheel just rolling back and forth on a track. This really shows its unique job perfectly. It can hold up a massive amount of weight from above, no problem, but it's specifically designed to just give way if there's any horizontal movement. I know, it sounds weird, right? Why would you ever want part of your structure to move? Hold that thought. We will absolutely come back to that. Okay, so we've seen how these supports manage all the big forces on the outside, but now let's zoom in, way in, to see what's actually happening inside the materials themselves. Welcome to the world of stress. Now, in engineering, stress, which we show with the Greek letter sigma, isn't an emotion. It's not about deadlines or anything like that. It is a physical quantity. It's the measure of the internal forces that the tiny particles of a material exert on each other. You can pretty much think of it as internal pressure, and you calculate it by taking the force being applied and just dividing it by the area it's pushing or pulling on. And that internal pressure really only works in two main ways. First, you've got tensile stress. That's where the material is being pulled apart, kind of like a rope in a game of tug-of-war. Or you can have compressive stress, where it's being squeezed together, like a column holding up a heavy roof. So let's say a material is put under stress. What happens next? Does it stretch? Does it bend? Does it just snap in half? The answer tells us everything we need to know about that material's personality and whether or not it's the right one for the job.
This graph right here, it's like a biography for a material. Along the bottom you have strain, that's how much it's stretching or deforming, and going up the side you have stress. In that first straight part, the elastic region, the material will stretch, but it'll snap right back, just like a rubber band. But if you push past that yield point, you enter the plastic region. And now, any stretching is permanent. It's bent out of shape for good. If you keep applying stress, it'll eventually hit its ultimate breaking point and fail. And this whole idea leads us to two very important types of materials. On one hand, you have ductile materials, like steel. They have a big plastic region. They give you plenty of warning. They stretch, they bend, they deform, long before they actually break. But then you have brittle materials, like cast iron or concrete. They have a teeny tiny plastic region. They show almost no deformation at all, and then they just snap.
Okay, we've met our 3 key supports. We understand what stress is, and we know how different materials behave. Now let's put all the pieces of this puzzle together and finally solve the mystery we started with.
So let's go all the way back to our bridge and back to that weird roller support. We know it can handle the vertical weight of all the cars. That's fine, but it is literally designed to let the bridge move from side to side. Why on earth would you build in movement? I mean, isn't being stable and rigid the whole point?
And here it is. This is the absolute genius of the design. On a hot summer day, the steel in that bridge actually expands, and on a cold winter night, it contracts. Now, if both ends of the bridge were fixed in place, that movement would have nowhere to go. It would build up massive internal stress that could literally buckle or crack the entire bridge. But that little roller support allows one end to gently slide back and forth, safely relieving all of that thermal stress. It's not a bug, it is a brilliant, totally necessary feature. So, the next time you cross a bridge, take a look underneath. See if you can spot the supports. You'll see the fixed ones, you'll see the pinned ones, and now you'll know exactly why that one roller support is there, letting the whole thing breathe. The world is built on these clever connections, managing incredible forces we can't even see. I hope this gives you a new way to look at the world around you.